The Big Bang, the birth of our universe. Everything we see today emerged from a region smaller than a pinhead. The black hole, swallower of all things, including light, and warps in space and in time. These are some of the most extraordinary discoveries in science, and they're all explained by the work of this man, Albert Einstein, by his theory of gravity, General Relativity, which was announced to the world 100 years ago this month. To celebrate, we thought we'd explore the very, very strange universe that Einstein showed we lived in and show how his work is still driving science. We'll go to a 27-kilometre long underground tunnel in Switzerland, CERN's Large Hadron Particle Collider. We visit two remarkable 3-kilometre long rooms in Italy and see the biggest underground labs in the world. They're inside a mountain. We'll discover what these astounding facilities reveal about Einstein's extraordinary universe. We start our journey in Tuscany, a place famous for Renaissance artists. But these parts were also where the earliest scientific thinking about gravity began, by this man.
Galileo was the first person to think about gravity in terms of being a kind of universal thing.
Galileo Galilei lived in Pisa, not far from this Italian tourist icon. It's not a bad tourist attraction, but there's something far more exciting just around the corner. A few twists and turns through the back streets of Pisa, and there it is, the house Galileo was born in. Now that's a tourist attraction, the birthplace of one of the great men of science. Yeah, funny, no tourist crowds here. And the building's a real estate agency these days. But of course, that other attraction is one of the great icons of science too. Legend has it, it played a leading role in Galileo's theory of gravity.
Previous to him, it was thought that a heavier object would fall faster than a lighter object. You know, it was just kind of common knowledge.
By dropping different weight balls from the top, Galileo demonstrated they all hit the ground at exactly the same time. Now, Galileo's insight was pretty amazing. How on earth would you conclude that a stone and a feather are pushed along by the force of gravity at exactly the same speed? It doesn't appear that way because of air resistance, a force that pushes up against gravity. But remove the air from a couple of chambers, and this sponge and ball bearing accelerate at exactly the same rate, just as Galileo predicted. And we eventually had unearthly proof of his great insight that all objects fall at the same speed.
So an astronaut on the surface of the moon has dropped a feather and a hammer.
I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
Now, that's great confirmation for the traditional understanding of gravity. But I'm off to a place just down the road from Pisa, where physicists are again working at the cutting edge of gravity research. This time, they're searching for these things in the universe Einstein predicted 100 years ago, yet have never been found. And they're truly weird. Waves of gravity. Think about it. Waves of water make sense. They're ripples in water. But a gravitational wave is a ripple in nothingness, in empty space itself. In fact, it's a ripple in space and time, whatever that means.
Space and time, it's like rubber. You can deform it. You can have ripples. You can have distortions. You can have warpings.
It's just a deformation in the space-time. So it's like an angel that moves his wings.
To understand, you need to know a little about Einstein's general relativity. He showed why all objects fall at the same speed. It's because gravity is not really a force. It's kind of an illusion. Einstein's breakthrough was to treat space and time as actual things.
Before Einstein, space-time was like a theater where events took place, but it wasn't a player in the show. After Einstein, after general relativity, space-time does stuff. It acts, it warps, and it can carry energy. It moves.
Indeed, gravity is just warp space-time.
This can be thought of as space-time, so you have sort of a flat grid. So if you take something with mass,
So that could be the sun?
so it could be the sun, you can see that it causes this sort of dent, and it sort of bends the space-time. And so if you take something like this, maybe the Earth,
Yeah, okay.
and you stick it on this bent space-time, it'll go around in a curve, in a sort of orbit around this massive thing, because it's trying to move in a straight line, but the thing it's moving through is not flat.
So it's not like the sun has this force that's pulling it in. It's just that it's naturally going around because of the bent space-time.
In a sense, yes, things are trying to move in straight lines and just moving in the sort of most natural, shortest path, and that ends up being a curve if the space-time itself is curved.
And gravitational waves are just ripples in space-time. And they should be rippling throughout the cosmos. If we can discover them, they offer a picture of our universe way younger than anything we've observed before.
If we can detect them, it would be a remarkable moment in the history of astronomy.
To search for them, researchers have built this single room that's 3 kilometres long. Inside it is a single long tube. So this tube stretches 3 kilometres.
3 kilometers.
And inside the tube is nothing. A vacuum better than the one in space. They achieve it using ultra-high vacuum technology, just as they do at CERN to make the vacuum inside the Large Hadron Collider.
This is the largest ultra vacuum system in Europe. I'm just saying Europe because there are the other two machines in the United States which are longer.
Yep, the US has 2 4-kilometre long gravitational wave detectors. Who says physicists aren't competitive? So it's the second biggest vacuum in the world.
The second biggest, yes.
And bigger than CERN, more importantly.
Biggest than LHC because it's true that the ring of LHC is 27 kilometers long, but the volume is much more smaller.
CERN's not a vacuum, that's a vacuum.
That's the vacuum. We are challenging CERN. Yeah.
We'll discover why this ultra-vacuum is so important shortly. First, you need to see the big picture. So there's 3 kilometres of tube this way,
Yeah.
and then at right angles there's another 3 kilometres out that way.
Yes.
That's because the key to all gravitational wave detectors is to have 2 identical buildings at right angles to each other. When a wave passes, it bends the very space-time it moves through, temporarily changing the lengths of the buildings. Indeed, changing the length of everything.
Were one to pass through me right now, you'd see me get slightly taller and slightly skinnier one moment, and then the next moment I would get slightly fatter and slightly shorter.
When a gravity wave passes through here, the buildings stretching out to the north, 3 kilometres, might become ever so slightly shorter, whereas the building to the west could become that tiny, tiny, tiny bit longer. And they can actually measure that difference. They do it by shining laser beams down those ultra-vacuum tubes. A single beam is split in 2 and is reflected back and forth between mirrors. If those laser beams become even slightly out of sync, it means they're travelling different distances, and so the buildings must have different lengths, caused by a gravitational wave. To give you a feel for how precisely this equipment can measure distances, one atom is less than 1/1000th of a metre across. Well, they're measuring distances that are 1/100000th the size of an atom.
So that's tiny. It's incredible that we can even imagine ever be able to experimentally determine these changes.
But we can. The key is to keep the mirror laser system rock steady. Even the vibrations from distant traffic must be blocked out. And that's where that ultra-vacuum comes in. Sounds from the vibrations can't travel through the vacuum in the tube, just as sound can't travel through the vacuum up here. That's why no one can hear you scream in space. And other vibrations must be kept out as well.
If there is an earthquake in Japan of quite large intensity, our mirror oscillates. So we have to take care about that.
They do it by hanging the mirrors from 10-metre-long chains of heavy pendulums like this one. Physics demands, as you move down the chain, vibrations are steadily reduced by a factor of 10 million billion at the bottom.
So that isolates the equipment from pretty much everything. Maybe our mirrors are the most quiet object in the universe.
The mirrors themselves have to be near perfect, hence clean room construction. The first thing you notice is you can't even see your reflection in them.
This is one of the mirrors. It's completely see-through, I hear you say. Now that's true for visible light, but for infrared radiation, and that's the wavelength the laser operates at, that surface is almost completely reflective. 99.9999% of the laser light is reflected back.
The gravitational wave detector will be finished and gathering data from space in the next 2 years. Different astronomical objects give off different patterns of gravitational waves.
So if you actually take a gravitational wave signal and convert it into an audio file of a binary black hole system, it sounds like this. And that's a chirp.
And other objects emit gravitational waves too.
These waves need very large mass concentration and very peculiar phenomena.
One of the most peculiar phenomena is a neutron star.
It's a terrible object. Imagine to have the sun and shrink it to a diameter of 10 kilometers.
Given our sun is currently 1.5 million kilometres across, that 10-kilometre ball would be an extraordinarily dense dead star. A handful would weigh as much as a mountain. And these stars can spin up to 700 complete rotations every second.
And they would sound more like a pitchfork being struck, something like boop. Supernova, on the other hand, exploding stars are messy, complicated events, and so they would have a dirty sound in a short duration and maybe sound like.
In the future, with detectors in space, we might eventually even pick up the gravitational waves from the Big Bang itself.
These gravitational waves from the very beginning of time, when the universe was less than 1 second old, are probably still around with us today.
Detecting them would be a stunning confirmation of Einstein's extraordinary universe. Einstein lived in several countries, but his longest citizenship was to this one. We're visiting to find out about one of his theory's most dramatic implications, the Big Bang.
We've come to Switzerland to visit physicists who are studying the Big Bang by creating their own mini Big Bangs. And to do it, they're using the biggest machine on the planet, the Large Hadron Collider.
The heart of the machine is a long circular tube with, I guess, the third best vacuum in the world. Inside it, subatomic particles rush around, colliding at almost the speed of light. Actually, I first visited CERN in 2008, before it was switched on. Then it was safe to go down into the tunnel. Emmanuel Tesmulis gave me the grand tour on very dodgy CERN-issue bikes.
So if we just keep riding, 27 kilometres, we'll eventually come back to where we are.
Yeah, we'll come back here. We're about 100 metres underground as well. That's the other thing we should not forget.
Yeah. I mean, it's a massive, massive construction. 27 kilometres of this high-tech equipment.
I think what you're looking here is probably the most advanced scientific instrument that we've ever constructed.
The advanced instrument smashes protons together. They're just atoms of hydrogen that have had their electrons stripped off. And the smashes occur at incredible speed.
Now, this really is mind-boggling stuff. Inside here, there are protons whizzing around the circuit. And they travel in bunches. There's about 100 billion protons per bunch. And there are a few thousand bunches spread around the whole 27 kilometres. Now, they're travelling at 99.999999, that's 8 nines, % of the speed of light, and then they're brought into a head-on collision.
Now, for the last couple of years, they've had the Large Hadron Collider switched off while they soup it up and get it ready to turn on at full energy. To find out what they've been doing to the LHC during shutdown, I caught up with Emmanuel again. Hey, Emmanuel, how are you?
Graham, welcome back.
Yeah, 7 years I think it's been.
Welcome back.
Thank you.
And I hope you can see a lot of new things after 7 years.
All right, let's have a look through.
Okay.
The key changes they've made involve these superconducting magnets, which are the backbone of the LHC. They steer the beams of particles around the 27 kilometres, and this is just one of them.
And as you can see, it's about 15 meters in length. Each one of these magnets weighs about 35 tons, and there's 1,232 of them in the machine. So it's not a tabletop magnet. You can't put this on your fridge, well, unless you have a very big fridge, right?
They're special because when cooled to minus 271 degrees, they're superconductors of electricity and so can generate enormous magnetic fields. The main job during shutdown was to upgrade the connections between the magnets so they could handle the LHC running at full operating strength.
These interconnections between neighboring magnets, these are superconducting interconnections to transfer the current all around the machine, and currents are reaching up to 12,000 amperes.
That's some current. Just 1/5 of 1 amp is enough to kill you.
Elizabeth, hi. How are you?
Yeah. The LHC has been turned back on, and the scientists are, well, like kids waiting for Santa.
And that's what's exciting. Again, it's like, having Christmas. And you have a box with a present, and you don't know what it is, and you get excited and say, no, you cannot open it for Christmas.
This is where the real pressure was during switch on, the room that runs the Large Hadron Collider. This is mission control for CERN. Mike Lamont's the boss, ultimately responsible for keeping the LHC working. I mean, it looks like a complicated machine.
It is complicated. You go down there and you look at it in some places and you just shake your head and, it's just amazing that it ever works at all.
It takes up to 13 operators, plus their technical assistants, and the pressure not to make a mistake is enormous, because that beam of protons in the tube travels with the energy of a high-speed train.
You've got collaborations of 2,000 people out there, and they've spent their careers building these precious detectors, and they do not want us, sticking beam in them.
No wonder they celebrate each success.
It was tough in 2008, it was tough in 2010. I mean, that was, my gut's still not up thinking about it.
This latest restart was relatively easy. Mike's got used to the pressure. When the protons smash into each other, it's like creating little big bangs, possibly leading to a new understanding of gravity, even beyond Einstein.
The conditions of the collision are simulating those conditions really at the outset of the universe, 13.8 billion years before. So it's like a millionth of a second after the time zero.
Indeed, CERN's created little bangs that are the hottest conditions ever made by humans. More than a staggering 4 trillion degrees. That's 1 billion times hotter than the surface of the sun. With the machine running at full bore, the scientists are hoping to create yet more particles new to physics. Indeed, they might even create an extremely exotic one. It's a remote possibility, but in principle, you could even create a micro black hole.
If we're lucky, we will. They will decay very quickly. We will not see the black hole itself, the microscopic black hole, but we will see the decay products, a splash of energy in our detector. Terribly exciting if we do. Probably even more exciting than discovering the Higgs boson, in a way, because it's something which it's really out there.
We looked for these also in the previous run, but we could not reach the energy high enough that we are going to reach now. So now we can probe if that black hole exists at a higher energy.
Theory says if we can create microscopic versions of these, the universe must be very strange indeed, with extra dimensions and possibly even parallel universes. That would make the universe even more extraordinary than perhaps even Einstein imagined. Now, of course, no special on Einstein would be complete without asking, could Einstein have been wrong? Well, some physicists say not so much that he was wrong, but that his theory was incomplete. And their argument involves something very mysterious sounding, dark matter.
Dark matter is one of the biggest mysteries in physics.
We can see its effects, but we just don't know at all what it really is.
Ordinary matter is what everything we see is made of, stars, planets, you and me. Dark matter is a proposed different kind of substance. It's all around us, even down here on Earth, but it's invisible, indeed ghostly. Dark matter particles pass straight through everything. In a second, about 1 billion pass just through the palm of my hand, and of course, I don't even notice. Scientists deduce that dark matter exists because of the way our galaxy spins.
As it turns out, the Milky Way is rotating way too fast. The stars are whizzing around like crazy. So, you know, the whole thing should be blowing apart.
Our galaxy's not blowing apart because the combined gravitational pull of all the matter in it holds it together. The problem is, there's not enough ordinary matter to provide sufficient gravity. There must be another source of gravity.
So where does that gravity come from? We don't see enough matter for that gravity, so we say there has to be extra matter. That's dark matter.
Indeed, to provide enough force, the dark matter particles must outnumber the ordinary ones 5 to 1. So it's sort of the dominant matter, and we have no idea what it is.
That's right. That's right.
Isn't that disturbing?
No, it's great. It's a fantastic opportunity. I mean, it's like, my God, we know it's there. You know there's this huge uncharted territory. You just have to go there and start charting it.
But do we know it's there? A small number of critics say we could get rid of the whole idea of dark matter by changing Einstein's equations. So could Einstein's relativity be incomplete in some way?
Well, we don't know really, because although the theory of general relativity has been tested very precisely on relatively small scales, what if it fails on very large scales, on the scales of galaxies or clusters of galaxies? So some people say that this might be the case, and what we attribute to dark matter in the universe is actually a failure of gravity, and Einstein was wrong or not totally right.
So, physicists are desperately searching for dark matter beneath these Gran Sasso Mountains in Italy. Inside are the biggest underground labs in the world. They're so big, you can't walk to them from the offices above ground. You have to catch the courtesy bus, which heads out just on the regular freeway, complete with regular toll booths. Through a tunnel or two, and eventually you come to a strange turn-off. You half expect to see a character from a James Bond movie here. Now, the key to a dark matter detector is shielding, because to pick up the faint signal of a ghostly dark matter particle, the detector has to be shielded from all stray ordinary matter particles. That's why the labs are underground. The surface is continually bombarded by radiation.
For example, although we are mostly unaware of those, there are very high energy particles coming in from space called cosmic rays.
The 1.5 kilometres of rock above filters out most of this space radiation. The ghostly dark matter particles, of course, pass straight through.
Hey, Jacques, it's Graham.
Nice to meet you, Graham.
Yeah, likewise. What a lab.
Yeah, it's quite an impressive facility.
I've seen some impressive labs in my time, but this one takes the cake, I think.
This is one of the experiments to detect dark matter. It's called the Xenon experiment. 3 stories of high-tech gadgetry, although much of it is further shielding for the detector.
So this whole chamber will be full of water?
Yeah, the idea is to provide additional shielding.
The detector will sit in the middle of this tank, and the surrounding water will block more natural radiation from the rocky walls inside the cavern.
And is that just regular water, or do you need special water?
No, we'll be filling this with deionized water because we want the water as pure as possible. We don't want the radioactive backgrounds from the water itself getting into the detector.
Right, so you've got a shield from the natural radioactivity in water?
Yeah. Every single piece that goes in the detector is also being screened individually, so we know how radioactive it is, and we can account for that when we're doing our data analysis afterwards.
Some detectors in this magic mountain of experiments use lead for additional shielding. Of course, it has to be pure too, so it comes from an unusual source. This is a lead ingot made by the ancient Romans. For the last 2,000 years, it's been sitting at the bottom of the sea in a shipwreck, and it's only recently been recovered. Now, it turns out it's the most pure lead on the planet, perfect for making shielding for dark matter experiments.
That lead lost all of its radioactivity by sitting at the bottom of the Mediterranean, say, for the past 2,000 years.
As well as shielding, a lot of the infrastructure is pipes and tanks, because a special liquid is used as the detector, a large vat of the chemical xenon. Basically, the xenon atoms just sit there, waiting for a dark matter particle to collide with one of them. When that happens, a detection's been made.
So if we come up here, we can see the center of the detector, where the actual science will be happening.
Ah, yeah. Okay, so the liquid xenon is inside there.
Yes, correct. We have the outer vessel, then inside that we have a slightly smaller stainless steel vessel, and it's in that inside vessel that we'll fill up with the liquid xenon to look for the dark matter events where all the instrumentation will sit.
Now you might be wondering, if dark matter particles pass through everything, won't they just pass straight through the liquid xenon detector?
Vast majority of them most likely do. The idea is that's why we build the detector as large as possible to try and increase the chance that one of those particles will eventually interact in our detector.
Very occasionally, a dark matter particle will collide with an ordinary matter atom, like a xenon atom.
And we're looking for that one single one in a year that might interact.
Making even one detection would open the door to some extraordinarily exciting possibilities.
Look, there's so much more dark matter out there than normal matter. And look how rich our world is. And so you begin to wonder, if I have 5 times more stuff, what wonders could be hidden in this dark universe? You know, there's absolutely no evidence whatsoever that there would be dark planets and dark people wandering around. But there's also nothing that says that this can't be.
It's speculative, but our world could be surrounded by a dark matter parallel universe without us being aware of it. While we haven't found any dark matter yet, most physicists believe it does exist.
The fact is that we have so many different lines of evidence pointing to dark matter.
So Einstein's theory is probably safe. Indeed, dramatic new confirmation for his work would come with the first detection of gravitational waves.
That would be a huge discovery. That would just be mind-blowing. By all expectations, we will live to see that happen. The experiments are getting really close to do that.
Indeed, the American detectors have just been switched on. We could pick up a gravitational wave any time.
Until now, we've been completely deaf to these gravitational wave sounds. So we will be hearing the symphony of space-time for the very first time.
Not only would Einstein's 100-year-old prediction that gravitational waves exist have been proved, a whole new window on our universe would open up.